So in the rest part of the tutorial, the objective is to introduce or reintroduce the security concepts, and then showcase some of the code base that already exists or and will exist in the future, or with some comments. And so my part is about data authenticity. Then we're going to move forward to kind of how to bootstrap trust in an environment. We'll have a few introduction of the command line tools that kind of we have in the code, how we generate keys and so forth. And then we have a small part, not small part, another big part for kind of demonstrate name-based access control. I already showed a little bit in the previous tutorial, but then G will be talking a little bit more detail and also introduce additional things. Okay, so this is kind of the same slide that Lisa just showed, and kind of my objective is to introduce this sign-in and verification part. Kind of with a small kind of caveat that mostly it will be for the verification. For the signing, kind of conceptual is all what I'm saying is applying, just not necessarily the same exists in the code base. Okay, so we talked today a lot about the data-centric security or like data centricity, and effectively what we actually talking about is kind of the first is foundation block for data-centric authenticity, which kind of build on top of which we can build additional things like data kind of secrecy of the data, and we can have like a name authenticity, secrecy, and so forth. Privacy is slightly different question. It's not necessarily data-centric. And again, reintroducing the basic concept that in NDN packet, we have a name of the packet, kind of a content packet, and whatever signature. And in addition to kind of these three elements that kind of cryptographically bind the content and the name, there is also the important piece of information is a key locator, which effectively identifies what is the key you need to fetch in order to verify this data. And that key, I mean that name, referring to another piece of data, like another data packet, that they just happen to carry the public key as part of the content block. And again, it has its own key locator block, and pointing to another key that in order to verify, and at some point it get into so-called the trust anchor, so kind of something that is probably self-signed, but or something else. So this is the basic concept. So effectively, with each data packet comes not responsibility, but rather like a certificate chain, or like a chain of something that in order to verify. So it's kind of a great idea, and logically, or kind of, if you just look at this, you just, oh, I will get the packet and verify this whole chain. But the thing is, not all signatures, not all keys are actually the same. And you know about that in the HTTPS world, where you don't really want to trust some random self-signed certificate if you go to the bank website, or like if something doesn't match. So in NDN case, it's something similar, but actually we can do it in much more granular and much more flexible way than we can do in IP. Or actually, we cannot do it in IP because IP is just IP addresses. We do it in HTTPS, which is kind of relying on DNS names. So we're kind of stripping out all this complexity of multi-namespaces. We're using single namespace of NDN and leveraging, can leverage different parts of the hierarchy that I will try to show off a little bit later. But in this kind of basic example, is just if data is signed by the camera, like if it's a camera in home and it's signed by the so-called trust anchor of the home, then probably it's a good data because kind of the first names match and then the cryptography also matched and the signature is actually valid. Kind of, it's a possible signature and it's a valid signature. In the other case, when Mr. Heisenberg signed that specific data packet, then kind of pretending that it's a kind of a good data packet, and crypt is probably also working, and you may even have this thing installed as part of your trust anchor. But the policy may simply prevent this data be valid just based on the name. So the Heisenberg thing is for the movies or for the actual blue stuff, but not for random camera videos. And you can build some arbitrarily complex in signature chains and put the arbitrarily complex, strict but complex the restrictions so that you say this data name with this structure has to be signed by the key that has this structure. And this is just a small example, and I'll try to expand on what exactly I mean by the structure of the name. And specifically, what I'm trying to emphasize that you can have a system where each key that's being produced has reduced power. So unlike current HTTPS keys that you simply get for the web browser and for the web server, and then all data that this server is serving is effectively signed by the same key, like an authenticate. I mean, it's not exactly data being signed by the key. It's kind of you create a connection and authenticate the connection, and everything that goes through this connection is kind of good, like and correct. And like you have the whole power of the whole namespace on that website specifically. But what we can do with names, like we can actually, because each data packet that's being produced has this complex name, and kind of each key has a name, you can actually play a game of names to restrict power, like what this key is supposed to do. So for example, let's say I have some kind of key that acting as a local trust, and I can delegate some other key with a constrained power. Like saying like the prefix of data have to match the prefix of the key. So if I make the bigger prefix of the key, then it only can sign the smaller part, I mean, it's unlimited part, but a smaller part of the namespace. So what I kind of have a few examples here. You can restrict based on some kind of location. If it's kind of home, you can define like whatever examples here, living room, kitchens, and first floor. You can, in addition or instead, define some kind of a data type of the data. You can add some form of dates or times, or kind of you can have different types of wild imagination. And this is just random part that I picked the living room restriction, and I kind of not semi-randomly designed this namespace. So for the key that kind of I'm assigning further, it's still my key because I'm generating like I'm still kind of using my namespace. But then I add in this restriction living room. So this key is no longer can sign or authorize signing or authorize commands in the whole house, but only for this part who is subject to the living room restriction of the context. And what I have here is kind of additional restrictions you can be imposed on the next level. So some camera that's installed at house can be given a key that's only valid for this specific camera, and not only for this specific camera in this living room, but also only limited for some part of the view of the house. And how it's enforced, it's a different question. But you can do some kind of limitations of the namespace in which this camera can publish. And I think I have one more. Oh, yeah, and one more is just the publishing actual data that is being signed by the previous key, that is signed by the parent key, with the assigned parent key, which effectively builds some kind of set of rules. And I have a kind of a more unified picture of this in a few slides. I'll stop, kind of breathe a little bit here and say, so this conceptually is a pretty cool idea. Look, you just put all these policies, you play with names, you can kind of restrict power of the keys, but you don't really want to do it manually. Like, so on one hand, you could just define some hard-coded policy that's saying, oh, this prefix of the data must match prefix of the key. So this part can be kind of hard-coded in some of the library. But even in this example, I'm not even using just prefixes. I'm still kind of doing some rearranging of the namespaces, because remember, NDN names are not just used by the application, they're also used by the networking layer. So you have to be network have to be mindful of what the application is doing, and the application has to be a little bit mindful how network delivers the packet, so like what kind of feed entries exist. So you have to that's why you not necessarily can just have a prefix match. But then at the same time, you also don't want the application implement very complex logic for the key matching. So that's kind of a basic idea behind the work that we published, I believe, in 2015, and it has been kind of evolving since then. And there's some other code base before that, and there's additional code base that being developed but not yet merged. So kind of the presentation will be showing one syntax, and then I'll show actual example that uses slightly different syntax, but kind of the conceptual is the same thing. So there is some form of a language, a very simplistic language that effectively defines some form of rules to match data name and a key name. And effectively, these rules apply to the name components. So like you define like set of this name components have to match the set of the other components. And kind of as you can see, it's more or less regular expression-like syntax for the actual name matching plus the additional ruling, as I will show in a few seconds. Okay, so let me try to go over kind of some motivations or some ways you can use this trust schema language to define a rule. And there are actually a few ways you can do that. So one kind of simplest way, you say, here's the name of the, okay, in this case what I did. So this is for my living room key and kind of restriction based on the trust anchor. So this is kind of extremely simple thing. So I'm saying that this key that has a home prefix, home, then users, then some kind of a username, then the living room as an entity and kind of key and key ID component, and have this thing, like this exact format of the name, have to be signed by the local trust anchor. This is perfectly works, but not generally enough. So you can actually define it in a slightly different way. Instead of defining that this key has to be, this living room keys have to be signed by something, and then the kitchen key have to be signed by something, and then some other place they have to be signed by something. You can just kind of replace that thing with the general statement. Kind of, this is like regular expression syntax for wildcard component with kind of when assigning some specific name for this name component. So now anything that starts with home users has some username, and then any kind of a location as a one name component, and then key can be possible combination for the signing purposes. And you can actually go even further by not just restricting to this rule to be applied to the home environment with like home users, but other just kind of generalizing this prefix, saying, oh, this any kind of prefix user and username location can be signed by the local trust anchor. So this was for the just first level, like trust anchor, the first keys, and this is just the circles of power of the keys. Like each key has a less power for the namespace, as you can see in the slides. And I have just the basic examples for the other keys, but kind of the structure is exactly the same. I'm just rearranging things in different ways. So kind of defining what the name of the data of the key of the interest, and then kind of using parameters that was extracted from the name to parameterize the actual rule of the next level key or next level data packet. Okay, so that's for the, and this is for the actual data name. And kind of, this is kind of the summary of kind of this effectively 4 rules. And what I'm kind of trying to lead to is the first 3 rules that I defined, they apply for any kind of, they apply for this application being deployed in any environment. Like if it's my home, this is home, just some prefix that I happen to own, or if it's like Alex home, G home, or like dishes home, or whatever, some prefix, it still applies. And but it will not work until you configure this so-called trust anchor. 1 second. But actually, I finished. Yes.
Sorry to interrupt. Your schema seems to really be sort of a hierarchy of scope.
Yes.
Of trust. Are you treating roles separately? Like what you can do?
Treating what?
Roles. Like you had talked in your example about a user might be able to administer a camera versus view a feed from that camera. Are you considering those to be different paths down this schema, or is there a different mechanism for specifying the kinds of actions that you can do if you have a certain?
So part of the answer to this question is you could try to define a schema that have the kind of role-based name matching. This may not necessarily work, and potentially we may need some form of extension of this simple language to define a bit more complex role-based rules. But we have thought initially about this, but even this is already complex. And but we definitely need to work on that part. Yes.
So regular expressions are easy to screw up. So if I make a mistake in regular expression, what does it mean? I give extra credit?
I mean, so there are two types of mistakes that you can make. So one type of mistakes you unfortunately give you will either authorize people who are not supposed to be authorized, or you verify data that's not supposed to be verified. So this is one type of mistake that you can make, as with anything. But the other type of mistake, which is, I think, at least for me, more common, is the opposite. That I have a valid data that I thought I wrote the rule correctly, but in reality I didn't. And and I actually have an example of exactly this process. Because writing the rule is kind of an art at this stage. And this is kind of with the looking forward, what's supposed to happen in the future is we have a kind of looking forward and kind of actually exemplified in here. Hopefully we have a pre-created set of rules that apply in different applications. So for example, this is the application, the trust schema for application that can be deployed in home environment. And okay, this is a very trivialistic one, but hopefully we can define, or like an active security expert can define really secure trust schema that applies for the HVAC, with the thermostat, whatever, something in the walls, and all this environment being treated securely. So ideally, in kind of a long term, the developers of the application just pick the trust schema, or deployers of the application pick the specific model, or it picks specific modules of the trust schema, and then define the trust anchors or set of trust anchors, and then everything magically works. As of right now, it's yes, there is an art to define the trust schema. One thing that so what I have been talking at this point was for the verification part. So given this name, you got the data. Okay, I'll just show this one. Given signed data, there are like a set of rules that have been executed by the computer using the trust schema as input. This automaton or whatever the machinery requests the necessary keys following the key locator if those keys actually can sign the data, like using this name, and then doing the actual verification of the cryptographic signatures, and kind of giving the answer yes or no. So this is what we have in the code, which kind of straightforward process, which is the other process that we have been thinking for a long time. There's initial code, but it's still kind of a bit more complex procedure, is the opposite direction. Because given this, the same trust schema actually defines both. I mean, it defines how the data will be treated, how to verify the data effectively. And if you generate the keys that actually match the trust schema, then you can sign the data properly in a proper fashion, and so it can be properly verified. I mean, as you probably know, and like will be highlighted a bit later, you cannot really generate certificate on your own, because somebody actually have to approve you. And that somebody could be you, or could be somebody else, or could be some other device. So we have additional protocol, like NDN cert, that will be a little bit later, that provides help, provide the mechanisms for requesting the certificate. And actually, in addition to just requesting certificate, we use kind of, again, name game to define which authority we need to ask for the certificate. And that authority can actually be extracted from the trust rules themselves. But again, this is abstract. I don't have any specific examples how exactly to do it. And this is still ongoing work. But kind of ideally, this is the environment. We have getting some trust schema from somewhere, somehow, by some magic, like either some expert defines it, or we just grab it, like a pre-created one, plug it in the system, and the system plug it trust anchor as a bootstrapping point, and then system, whenever it needs the key, it generates a request certificate properly, and we probably some pop up some message on some our devices to approve some certificate or reject the certificate, and kind of we have a very high granular access, high granular keys, and each individual key have very small power to do bad stuff. So if some key is compromised, it only kind of affect that small portion of the namespace and don't really have a big impact otherwise. And of course, if like root keys have been compromised, that's a really bad story, but not worse than what we have or what we actually don't have today. Okay, so this is just a small summary. Remember, the names is a power of NDN. Like it's extremely important part. It's names is an art. There's still in many applications a really hard decision, and it's the first decision in NDN you have to make, like what kind of names, what is structure, and it's not always trivial to decide like which component to put where, and may not be necessarily a single answer to those questions. But if you do it, hopefully if you do it properly, then you can use this plain kind of name tricks to actually restrict access, or restrict power of keys in different ways. I have talked about the influencing the designs. So there is application consideration, there is network consideration. Now it's getting to the security consideration for the namespace design. For automation, I highlighted that for the verification, for the signing, and for the certificate management. Right now, I just want to have a brief highlight of kind of the actual syntax that we have right now. Like what I showed with the rules is kind of what we're going towards. And we have initial code, and if you have some free cycles, we'll be welcome to actually get you involved in this process. But what we have now conceptually is very much similar. It's just not as maybe not as strict as was defined in the system. But what we have is a simple thing. We have also a set of rules. It's just kind of they treat it independently in this process. So every time interest to data packet arise, kind of to the application that runs the validation, it simply tries to match one of these rules to this interest to data packet. So in this case, one rule is defined for the for interest, and the other rule defined for data. So the other part of the rule is filtering based on the name. So kind of you may have a different data that kind of or interests that are floating or that your application is being processed, and you may have different rules that apply to this data. So in this case, I'm kind of filtering all interests that start with home, living room, camera 0 control. So this is and defining what kind of relationship of this name to the name of an actual interest. So we have an option to be just prefix or exact match, or this is prefix, meaning that the actual interest name have to have a few more components afterwards. So that's kind of just matching that this rule will be try to match. And then we have a checker which actually checks what is the keylocator stuff, like something about the keylocator. In this case, so there are, again, there are a few options. One option is this simple name matching using regular expression. So in this case, I specify that there's a home controller. There have to be like these two components present in the keylocator. Then there can be something else, any component here, and then key, and again, some additional component. Another thing that actually matches a bit more to the trust schema, but even in a bit more obscure syntax, is a so-called hyperrelationship. And for the checker. And a hyperrelationship is simply trying to extract the pattern from the data name, extract pattern from the key name, and match them in some way. Like usually we use the kind of relationship to be equal, or again, or prefix. And what we're trying to achieve is a kind of, in this case, you can just write more general rule than what I just put here. Like this example effectively matches the first time I had mentioned the rule. So matches this one, when we have literally specifying the exact name of the key that has to be signed. Versus this hyperrelationship, which kind of trying to generalize exactly the same, but kind of with the effectively regular expression wildcard. So in this case, they just have to be one component, don't know which one. Then there's a key and something else, which has to be the part of the key locator. And a part of the data, it has to be some one name component here, and then followed by whatever number of name components afterwards. Doesn't matter which one. And then kind of this is standard regular expression that get in the group, that being grouped with the parentheses, and then trying to match them in some way. Again, this is not the same syntaxes. Probably they have completely different power, have potentially different characteristics. But you can see, like with this configuration file, you can right now you can, if you download the code, you can get this configuration file or some other configuration file and simply pass it to the validator. And now you have magically trying to validate meaningfully validated data packets. And I have a tiny demo in the remaining 1 minute. So we wrote like trivial consumer application and consumer and producer application, and kind of with a set of keys. So the producer doing kind of two bad things. One is producing good data signed by the good stuff, and producing good data signed by the bad stuff. Well, like good and bad data. And I want to just highlight, okay, so the application itself. Okay, just to showcase that the code that we have here is extremely simple. So we have some kind of a validator, like as an abstraction in the library, and we simply load that configuration file that, in this case, specified in command line, and then pass to as a constructor. And when we receive the data, we simply call this validate kind of interface, validate interface on this data packet, and simply specify a callback on when it's validated, or callback when it's failed to be validated, and kind of does it in this small program. But on the back end, it's doing all this logic, this complex logic of name matching and all other stuff, which I try to, will in a second, highlight by my example. Okay, so I will run it in two different modes, so you know a few tricks about NDN CXX library. So kind of that's kind of a few new additions that we had, kind of extra logging capabilities. So before it was just a library that you hopefully working, and for the security specifically, it was like, okay, so you give it the data packet and hopefully it works. In the worst case, not in worst case, but all cases are worst case. It's just giving you some random error that the packet is not validated. And you have no clue what exactly have not validated. Is it like the first data packet didn't match the rule, the second packet didn't match the rule? Is it the crypto validation failed? Like, it was kind of abstract. But anyhow, like let me run it in this way. So it was just, so it will show, so we're requesting some data using the, whatever this interest, getting data back. And in this case, this data signed by okay, it's supposed to be Heisenberg, but in this case, it's just NDN, EDU, UCLA, which are kind of not supposed to match, and we kind of receiving the validation failed result. But then I'm kind of running the same thing, that kind of producing next version of the data packet with the same prefix, which has a similarly correct key locator, and we have like validation failed. So if you don't know what exactly is happening, potentially you can think that this data packet is wrong. But in reality, in this specific case, this is something wrong with the trust schema. And you can have, so with NDN CXX library and kind of in NFD as well, you can enable different parts of the code that add additional logging capabilities. So, and the most helpful for me is this security logging. So I just enable all of security logging here. And you can just try to kind of see that there's actually a process that's happening, even though that code was extremely small, but nothing was there. In kind of on the back end, it tried to validate the data, tried to match the thing, trying to check. And in this case, it failed because the key locator is invalid. So it's see that this key locator is kind of wrong and doesn't match the home living room key. So kind of it just give up. But if I try to run it for the second time, then you'll see that's a slightly different picture. So it's still trying to validate. It's actually succeeded with the validation of the key name, and it wanted to proceed to the next step. But then something wrong happened with the next step. So it's trying to retrieve this key. It actually fetched something, but that what it fetched is actually not a valid certificate. It's kind of something on my local machine is wrong, that is not published in that certificate properly, and we kind of failed. And I have a few more rules here. Yeah, I think this one kind of a little bit simpler rule, like a little bit less points to make an error, even though it's a kind of not general enough policy. So this one's supposed to succeed in one case and fail in the other case. Let me try just rules. Okay, so now, again, the policy error. So kind of, we didn't even do the crypto validation at this point. It just failed because the key locator name doesn't match the policy, so there's no point doing anything. But then if you go for the other stuff, we actually succeeded with validation. So it's a policy matched, it found the trusted certificate, and everybody is happy and everything succeeded. Okay, I hope this is like a good starting point for the next demonstrations. What we plan to do right now is to showcase how exactly you can generate the keys, like how can you see in the system. Because this is NDN keys, we have to define our own tools, how to manage all of this stuff. Because OSX keychain not really helping us with this. We actually using on macOS, we're using OSX keychain to store the private key, but then we still have to store some public part of this thing, and the actual data packet in our own database.